Okay, this is video 4 on expected value. We're talking about uniform distribution. So essentially, I'm interested in finding the expected value associated with a uniform random variable. Right? So a uniform random variable, let's assume takes values from 1 up to n, right? So 1, 2, and so on up to n. And we know that the probability for each of these values is going to be 1 over n because they are equal, right? So that's how the uniform random variable is defined. And let me write the PDF, right? So from the PDF, I can calculate the expected value. So let's say the values are 1, 2, 3, and so on up to n, right? And each of these is equally likely. So this is 1 over n, 1 over n, and so on, 1 over n. Now to get the expected value for a uniform random variable is 1 over n plus 2 over n plus 3 over n and so on up to n over n, which can be simplified further as 1 plus 2 plus 3 and so on up to n. And the sum of this series here, 1 over n is half of, sorry, this is a dot, so I'm multiplying it, is half of n times n plus 1, right? So this and this get cancelled. This is essentially half of n plus 1. Or we can safely state that a uniform random variable on this 1 to n, this range, right? A uniform random variable on 1 to n has expected value equal to n plus 1 over 2. Okay, let's also look at the exponential distribution when we are interested in the waiting times, right? Let's also look at the equation for that. Okay, so just a quick reminder, the PDF for an exponential random variable where I'm actually representing my random variable in terms of the waiting time is given by this. It's beta and then 1 minus p to the t, where this beta was a constant. We just came up with this expression, right? So let me look at the most generalized form of this in terms of its PDF, right? So the waiting time will obviously begin from 1, 2, 3, 4, and so on. Let's say it goes up to some value k, and then finally up to some more value, I don't know. And then p of x for all t. So now I'm calculating it from the formula. Oops. Yeah. So I'm calculating it from the formula that I already wrote, which is beta times 1 minus p, right? Here it's going to be beta times 1 minus p squared, beta times 1 minus p cube, and so on. Same here. This is going to be beta times 1 minus p to the k. Right, again, going back to the formula for expectation, all I have to do is multiply t with this, right? So essentially beta is going to come out because it's there in every element, right? So this is going to be 1 times 1 minus p plus 2 times 1 minus p whole squared plus 3 times 1 minus p whole cube and so on. Okay, so even before we simplify this expression, we can consider certain series, the sum series that we already know, right? So let's consider those first, and then we're going to substitute them here, right? So let's consider these things. So consider this case 1 over 1 minus a. This is actually the sum of this series, 1 plus a squared plus a cube and so on. So these are like the sum of the infinite series. So similarly, this is also known that 1 minus a whole squared is actually 1 plus 2 times a plus 3 times a cube plus 4 times a4 and so on. Right? So all this information is known to us already. Now I can modify this 1 over 1 minus a whole squared by multiplying it by a. So if I multiply it by a, I'm going to get a over 1 minus a whole squared, and I'm multiplying a both sides, right? So here I'm going to get 1 times a plus 2 times a squared plus 3 times a cube and so on, right? So what if this a, we write it on the next slide, what if I substitute for a equals 1 minus p, right? So if I do that, I can actually substitute the same value for my series up there in this expression, in my expectation expression, right? So if I substitute instead of a 1 minus p, on the right hand side of this equation here, right, if instead of a I write 1 minus p, I'm essentially getting this part, right? So I can substitute that with the left hand side as well, right? So my expectation will become, beta will stay as it is, and then this will become times 1 minus p over p squared, right? And if I go and substitute the value of beta, which was already given to us, p over 1 minus p, we are going to get the expectation as 1 over p. Okay, so this is the standard value for the expected waiting time, 1 over p, which is like p is success. Let's quickly look at a small problem and then we'll move on to conditional expectation. So you shoot darts randomly at a dartboard trying to hit bullseye. Bullseye area is 1/100th of the board. So what is the expected number of darts you throw? Now the success here is to hit bullseye, right? So that's my success. And that is just 1 out of 100 parts, essentially, right? So this is my success. My P is 1 in like that entire 100th area, right? So the expected number of darts that I'll need, which is actually the number of times, right? So you can actually relate it to the number of times, is going to be 1 over P, right? Which is going to be 100. Right? So you have to, the expected number of darts that you should throw in order to get success is 100. Okay, so in the next video, I'll talk about conditional expectation.